or neutrino interactions with matter by Luis Álvarez Ruso. So, Luis, whenever you want.
Thank you, Juanjo, and good morning, everyone. This is my first remote lecture in a summer school like this, and I very much hope it's the last one because I feel that in a school like this, personal contact and interactions away from lectures is very important. It's perhaps more important than in seminars, certainly, and even conferences. But well, present circumstances are not going to stop us from spending the next hour and a half discussing neutrino interactions with matters. They matter so much to begin with because neutrino interactions are our doorway to neutrino properties, starting from detection itself, from the discovery of neutrinos, which is possible because neutrinos, after all, and even if weakly, interact with matter in the same way that nowadays the discoveries can be expanded by doing neutrino astronomy, thanks to interactions. Then we know that through charge current interactions, the flavor, the neutrino flavor is revealed, which is the key point to the study of oscillations. Moreover, matter effects are also a consequence ultimately of neutrino interactions with matter, and they are sensitive to the neutrino mass hierarchy. Obviously, neutrino interactions are also a key player in astrophysical scenarios and cosmology. This has been discussed at length in this school. I'm not going to dwell on this. Let me instead focus in the following scenario of neutrino accelerator neutrino interacting with the detectors. Those are mainly neutrinos with energies between a few hundred MeVs and a few GeVs. And in this energy region, the relevant interaction processes with the nucleons in the detector are, well, first of all, quasi-elastic scattering, in which we have a nucleon, not necessarily the same nucleon, the nucleon in the final state, but they are also inelastic processes, mostly meson production, and among the mesons that can be produced, the production of single pions is going to be the dominant one. In addition, all modern experiments use heavy targets to increase the interaction rate and increase the statistics. The materials have, many of them have carbon, different kinds of plastics, water, so they have oxygen, also iron, and more recently the detection technique using liquid argon has been developed. In the case of interaction with nuclei, all the processes mentioned before are possible. Now, what changes, what one should keep in mind is that these nucleons are no longer nucleons in the vacuum. They are not isolated. They interact with the rest of the nucleons through a mean field or forming correlated pairs. So all these processes, quasi-elastic, inelastic, on single nucleons or on nuclei, they are one could say they are all poorly known in general. But they are interesting. They are first of all interesting by themselves because they provide useful information about nucleon structure and nuclear response in the axial sector, which is difficult to obtain using different probes. Besides that, these processes are critical to reduce systematic errors in oscillation experiments. This includes neutrino flux calibration, determination and subtraction of different kinds of backgrounds, and neutrino energy reconstruction. So let me use this last item, neutrino energy reconstructions, as an example to elaborate a bit more the situation. So neutrino energy reconstruction is needed, first of all, well, because neutrino beams, because of the way they are produced, neutrino beams are not monochromatic. So neutrino beams are produced using accelerated protons that hit the target. They produce pions. These pions then decay, and therefore neutrino beams come with different energy distributions. Here are some examples of past, present, and also future elements, depending on the accelerator and the energy of the protons provided by the accelerator and the specific experimental setup. The range of energies is different, but as I said before, it's typically covers the range from few hundred MeV to a few GeV, up to perhaps 10 GeV in the case of the medium energy or the medium energy flux in Minerva. Now, that means that the neutrino energy is not known on an event-by-event basis. But this is a relevant quantity for oscillation studies, because as you know very well, the neutrino energy, the true neutrino energy, enters the oscillation, the expression for oscillation probabilities. And that means that in order to have this information, neutrino experiments should reconstruct the neutrino energy. Typically, this is done in two ways. One is the kinematic reconstruction, typical of low energy experiments like T2K. And in this case, what is done is that the neutrino energy is reconstructed using the information from the lepton, the final lepton kinematics in a charge current quasi-elastic or quasi-elastic-like interaction, right? So the angle, the lepton angle and energy are measured, and from there the neutrino energy is reconstructed, assuming that the interaction took place on a single nucleon at rest. Then there is the calorimetric technique used typically by experiments with fluxes in the higher energy range, like NOVA or DUNE in the future. And in this case, what the experiment attempts is to measure the hadronic energy that is deposited and add it to the energy of the final lepton. Now, any of these techniques is going to work reasonably well if we have a situation like the following. The neutrino hits the nucleus, but interacts basically with a single nucleon, a single neutron, and the rest of the nucleus acts as an spectator, so that by charge current interaction, a proton is knocked out. In this case, up to some smearing, the energy reconstruction is going to be okay. But if instead, for example, this proton that is kicked out rescatters with nucleons in the nucleus, it then loses energy and can, for example, then leads to a low energy proton and a neutron in the final state. And this low energy neutron can very easily escape detection. In this situation, what happens is that the energy reconstruction with either method is going to be smaller than the true energy of the event. And when this happens systematically, this can lead to a bias in the analysis of experimental data. So in order to deal with that, experiments have to determine a migration matrix from measured quantities, depending which could be visible energy, or could be just only the lepton information. So they have to migrate from these quantities to the true neutrino energy And to do that, the experiments rely on their Monte Carlo event generations. The best known one is Gini, but there are many others like Nuvro or Fluka. Now, ideally, these Monte Carlo generators are tuned to the best possible data. That implies that having near detector in oscillation experiments is crucial, but this is not the end of story. This is not enough, because you need really a reliable theoretical understanding and a realistic model of those interactions. If you have a Monte Carlo which has insufficient modeling of certain mechanisms, or even misses a reaction mechanism, as it has happened in the past, then even if you're tuning to data, the description of data will not be good enough. This will lead to tensions and ultimately to systematic errors. And this is actually the main message of this introduction, which is that, just to say it again, neutrino scattering mismodeling in event generators is a source of systematic errors, even if the generator is tuned to the best possible near detector data. And this is not just an abstract statement, it is something that is happening right now. For example, in the NOVA experiment, here, these are some results, recent results from NOVA, where you see the collected events as a function of the visible hadronic energy, and you can see that their Monte Carlo, which would be given by the sum of these contributions up to the red line, is not able to describe all the events, particularly at low visible energies. Now, at this point, the experiment has to tune the Monte Carlo, assume that some of the mechanisms are responsible for this difference. In the case of NOVA, they assume that there is that interactions with nucleon pairs called meson exchange currents. I hope I can get to that in the lecture later on. So this is the responsible for the disagreement, and they increase this mechanism by a factor of 2, which is a debatable decision. I am personally not at all sure that all this difference can be solely attributed to this mechanism, but there are no mismodeling in other parts of the Monte Carlo. But what happens is that once they are forced to tune rather strongly the Monte Carlo, in order to be conservative, they're gonna associate large errors with that tuning, and those large errors ultimately are going to increase the errors of the oscillation analysis. So again, we need, even if it is only for the sake of having precise oscillation results, it is very important to have good, realistic models of neutrino interactions with strongly interacting matter. And how do we do that? So in order to develop the theory of neutrino interactions with matter, we, as it could not be otherwise, we first of all rely on the symmetries of electroweak and of course also of strong interactions. Those very symmetries are going to help us relating neutrino cross sections, neutrino amplitudes with data coming first of all from experiments not involving neutrinos, with photons, electrons, or pions scattering on nucleons and nuclei, but also some of the available neutrino scattering data. First of all, on hydrogen and deuterium, even if they are old and with poor statistics, coming from all bubble chamber experiments, but also the information from the more recent information for heavy target can be used. Now, an interesting possibility, mostly for the future, is to use input from lattice QCD. Lattice QCD has its own systematic errors to fight with, coming from the finite lattice volumes in the simulations, the finite lattice spacing, the mass of the quarks involved in the simulation, which may not be the physical one. Actually, in general, it's not the physical one. There are also contamination of excited states. So there is a number of issues, but the field is progressing quickly, and I hope in a few years there will be reliable input from lattice QCD as well. So at this point, let me consider first of all the symmetries that are important for this kind of studies. So in this school, you have the lectures on electroweak interactions for the standard model in general. So I will be quick here. Let me just remind that the electroweak sector of the standard model after symmetry breaking can be written in this way, in which we have currents, matter currents, coupled to the vector bosons, which are the photon, the C, or the W boson. And each of these terms comes with its own coupling. Then in the leptonic sector, so the currents can be, so they are matter currents, they could involve leptons or quarks. In the case of leptons, well, I'm sure you know that the electromagnetic current is vector 1. Charge and neutral current interactions involving neutrinos have the typical P-A structure of weak interactions. And we have something very similar for quarks. For quarks, then we have the electromagnetic current given now in terms of fractional charge, which is 2/3 of or minus 1/3, depending on the flavor. And then neutral current interactions are written in this way here, where we have contributions from the weak isospin here, and also in the axial part, and also from the charges in this term proportional to the sine of the weak angle squared. Okay, so these were electroweak. Sorry, I forgot to mention an important point, which is that, of course, in the case of charge current interactions, we know that flavors are mixed, and this mixing is parameterized by the Kabibo-Kobayashi-Maskawa matrix, which, if we now remove the two heaviest flavors, the top and the bottom, this matrix is reduced to a rotation in terms of a single parameter, which is the Kabibo angle. So this flavor mixing in charge current interactions implies that we can, that by weak interactions, we can not only turn protons into neutrons and vice versa, but it's also possible to create strangeness. So we can turn protons into lambda baryons, or to produce single kaons. At the price, however, of having this amplitude suppressed by the sine of the Kabibo angle, which is small because this angle is small. Okay, so then coming to strong interactions. So in general, what we have in the standard model is that we know that QCD is a non-abelian theory, including quarks and self-interacting gluons, and because of this self-interacting, QCD is asymptotically free at large energies. This is the region where perturbation theory can be used in QCD. But as the scale reduces, we enter the effective decoupling increases. So alpha S increases, and the theory becomes non-perturbative, and we see confinement. So the quarks are not free, but confined into hadrons, which also means that if we are going to describe the physics of strongly interacting systems at low scales, the right degrees of freedom to deal with them is not quarks, but hadrons. But in order to model those interactions among hadrons properly, we have to take into account, we can't forget the symmetries of QCD. So what I'm going to do next is to discuss some of the approximate symmetries of QCD, of strong interactions. At this point, I'm going to focus on a reduced space of flavors. I'm going to consider only light S, D, U, D, and S quarks. Okay, so the mass of these quarks, even if the mass of the strange quark is heavier than those of the U and D and B quarks, those are still much smaller than the, say, typical hadronic scale that can be put around 1 GeV from the raw meson or the nuclear mass. So a very important approximate symmetry of QCD is the one that appears in the limit in which these quarks are all massless. So in this limit, one can see, so the QCD Lagrangian can be written in terms of left and right fields in this way. So the mixing between left and right comes only from the quark, the quark mass terms. So if this term is 0, the theory is symmetric, symmetric under SU3 left cross SU3 right rotations. As a result, we have 8 right current and 8 left-handed conserved currents. 8 simply because this is the dimension of the associated, the Lie algebra associated with the SU3 Lie group. And this conserved right and left conserved current can be rewritten in order to get the same number of vector and axial conserved currents. Now, even if small, these masses are not 0. So this symmetry is, to begin with, breaking. Sorry, I forgot to mention that these lambdas here. So many of you have guessed that these lambdas here are the Gelman matrices we use here. Okay, the 8 of them. So then we know that this symmetry is, to begin with, is explicitly broken. You can see the way in which this symmetry is broken by the mass terms in these two expressions. So here we have M is the mass matrix, which is a diagonal matrix with the masses of the U, D, and S quarks in the diagonal. And in the case of the vector current, the divergence of the current is proportional to this commutator of the mass matrix and the Gelman matrices for each of the current. And in the case of the axial current, we have a similar expression, but with the anti-commutator instead of the commutator, and a gamma 5. So this symmetry breaking, explicit symmetry breaking pattern tell us to begin with that in the case of equal mass, if all these three masses are taken to be equal, then the vector currents are conserved. Simply this M becomes proportional to the unity, so that this commutator goes to 0. So in this limit of equal masses, the vector currents are conserved, but the same doesn't happen with the axial current. So the axial current can only be conserved if we are in the chiral limits, if the masses are 0. This is known in the literature as partial conservation of the axial current. Now, the fact that if we have equal masses, the vector current is conserved is an important observation that led to the development of the quark model, right? Because it is an expression of an SU3 flavor symmetry, which again is especially historically, it was very important, although it is broken at the 20% level because of the difference, because of the fact that the strange quark mass is large compared to the U1 and D1. So, and this symmetry, this 20% breaking can be seen, for example, in the differences in the masses of the low-lying baryon, which are of the order of a few 100, 200, 300 MeVs. If we now restrict to two flavors, U and D, then we have a much better symmetry. In this case, we have a global SU through symmetry, which is broken only at the 1% level, which is again a consequence of the fact that taking those two masses as equal is a very good approximation. And so this SU through SU2 symmetry is nothing but the good old isospin symmetry. And in this case, instead of 8, we have 3 conserved vector currents that can be written now by replacing the Gell-Mann matrices by the Pauli matrices. So at this point, let me say a few words about the flavor structure of electroweak currents. This is gonna be relevant for what was coming afterwards. So again, so recall this is the structure of the electroweak Lagrangian. The electromagnetic current, we can rewrite these terms and keeping only SU and UD and S quarks, and we can rewrite this current in terms of the two diagonal currents that we have. So lambda 8 and lambda 3 are the only diagonal Gell-Mann matrices, and the electromagnetic current is diagonal in flavor. So we can write this in terms of lambda 8, and I'm calling this current hypercharged current, and in terms of lambda 3. The neutral current, which is also diagonal in flavor, can also be, leaving aside the strange quark contribution, can also be written in terms of B3 and By. Now, the charge current instead, if I take, for the sake of the example, only the U and the transition between U and D quarks, it can be written instead of in terms of lambda 1 and lambda 2. So those are flavor B1 and B2 currents. And if we now go back to the Gell-Mann matrices, we can see that lambda 1, if we look at the upper left corner of lambda 1, lambda 2, and lambda 3, what we see is the block corresponding to the Pauli matrices. And in the case of lambda 8, what we have in this corner is the unity matrix. So this reflects that if we consider only U and D quarks, the electroweak currents can be written in terms of 1 isoscalar and 3 isobector currents. Okay, so the same can be done with the axial current. Now we don't have electromagnetic current, we don't have any isoscalar contribution, but again, ignoring strange quarks, the charge current and the neutral current, axial current, can be written in terms of 3 partially conserved flavor currents. This is going to be important for it will appear later on. So let me now go back for a moment to chiral symmetry. So we discussed the explicit breaking of chiral symmetry, but this is not the only and not the most important way in which chiral symmetry is broken. If we actually take a look at the ground state of QCD, we realize that the spectrum is not consistent with chiral symmetry. An easy example is to take the light text vector and axial vector mesons, which have both spin 1 and opposite parities. We can see that their masses are very different. And in this case, these mesons don't contain heavy quarks, don't contain strange quarks. So this mass difference cannot be explained only by explicit symmetry breaking. So what we are seeing here in this example is the known experimental fact that chiral symmetry is broken in the spectrum down to an SU3 vector symmetry. And this spontaneous symmetry breaking has Goldstone bosons, which are the pseudoscalar mesons, the pion, the kaon, and the eta. So this, using this chiral symmetry breaking pattern, it is possible to write an effective theory in terms of hadronic degrees of freedom, which takes into account this symmetry breaking pattern. I don't have time here to explain how this theory is built in detail. I would just at this point like to highlight the fact that although he's known mostly for his contributions to the development of the standard model, Weinberg also made seminal contributions to the development of effective theories in general and effective theories for hadrons and the modern effective theory of strong interactions. So I think it would not be exaggerated to say that last Saturday, not only science, but humanity lost one of its best minds. And well, nonetheless, life continues. And as I said, I don't have time to discuss the structure of this Lagrangian. Let me just mention two things. First, that when one is looking at processes that involve small momenta, then it is possible to use this effective Lagrangian to do perturbation theory. Okay, this has a limited range of applicability, but it's, let's say, the best and most systematic way of discussing hadronic interaction, also involving electroweaves. Now, let me, as an example, consider just the simplest contribution to the axial current in terms of mesons, only with meson fields. So this contribution to the axial current comes with a pion field, for the sake of the example, and a derivative coupling of this, and a derivative of this field. This actually ensures that if we now take the derivative of the axial current, this will give a pion mass square, which means that in the chiral limit where this pion mass goes to 0, the axial current is going to be conserved. Then, because of this structure, we can write the matrix elements that connects the pion state with a QCD vacuum, and it's going to be parameterized in this way in terms of the pion momentum and a constant f pi. So this matrix element is what allows to describe pion decay, weak pion decay. So this is a textbook example. I'm not going to go through the details of this derivation. It's given here in the next 3 slides. Let me just highlight a few issues here. So first of all, as I said before, now we cannot describe pion system in terms of U and D quarks. We are in the non-perturbative regime, but we know from the symmetries of QCD that the pion field couples directly to the W boson, and that this coupling is via the pion form momentum. The second issue I want to highlight here is that now the W propagator now has in the denominator this 4 momentum square, which in this case corresponds, is just the pion mass square. And this pion mass is much smaller than the W mass. Therefore, the static limit in which this propagator is just written in terms of the W mass is a very good approximation. One can then combine this W mass square here with the 2-weak couplings that appear in the amplitude and write all this product in terms of the Fermi constant. So this is a construction that is going to be valid for all the examples I'm going to be discussing today. So except in the very high energy and momentum transfer, we can use this approximation and write cross sections directly in terms of the Fermi constant. Okay, so then let me, with these ingredients, one can go on and calculate the decay rate, the pion decay rate. This is the final expression that one gets. And it is written in terms of F pi, which means that by measuring the pion lifetime, it is possible to obtain F pi, which is called pion decay constant for obvious reasons. Now, the last fact I want to mention in this example is also well known, but very interesting, is that one naively would have expected the decay rate into an electron antineutrino to be larger for pions, simply because the pion is lighter, the electron is lighter, and the phase space available is larger. This can be seen from this factor here. You can see that if you now replace this muon mass by an electron mass, this factor is going to be enhanced. So the fact that the decay into electron and electron antineutrino is suppressed has a dynamical reason, and it can be understood if we realize actually this plot is for the opposite charge, but never mind. So the idea is in this case for pi plus, in the rest frame, this is a scalar particle. So the neutrino, which is massless or nearly massless, the emitted neutrino is left-handed. So in order to conserve helicity, the emitted positive muon has to be also left-handed, which is actually not the natural helicity that the lepton would have if it were massless. So therefore there is a helicity flip involved, and this helicity flip comes from mass terms, because as we saw before, mass terms are those that change, that connect left and right fields. So this helicity flip brings this muon mass square here that is ultimately responsible for the fact that the decay width to the muon flavor is larger than the one with electrons. Okay, this is a good point to make a short break and ask if there is any question. So if there are no questions at this point, let me discuss cross sections. But before looking at specific examples, let me make a few statements about cross sections in general, specifically cross sections of leptons, scatterings on nucleons, or even nuclei, because what is presented in the last few slides is general enough. It can be it's valid for both nucleons and nuclei. So we have this situation in which, again, a lepton scatters on a nucleon, and then there is another lepton in the final state. Could be a charged lepton, could be a neutrino, in the same way as the initial lepton could be both an electron or a neutrino. And then there is a hadronic state, which in this case we don't resolve. We are assuming that we are inclusive in the hadronic final state. Then the interaction is electroweak, so either a photon or a weak boson is exchanged, and it carries a momentum transfer Q, which this Q square in this kind of scattering processes is always negative, and I will be using sometimes the capital Q square indicating the corresponding positive quantity. So in this situation, the semi-inclusive cross-section in terms of the lepton variables can be written in this way. I have already assumed that this is in lab. So this is for the case of charge current interaction. So we see here that we have the Fermi constant square, and then we have the contraction of a lepton tensor and a hadronic tensor. So the lepton tensor is obtained directly from the lepton currents, and it has this structure here with a symmetric and an anti-symmetric part. In the case of electromagnetic interactions, only the symmetric part is present. So the anti-symmetric part appears when we have neutrinos, and it comes from the interference terms between the vector and the axial parts of the current. Then if we want to write this cross-section for electromagnetic interaction, all we have to do is just keep the symmetric part here and replace the coupling by this ratio of the structure constant square and the 4 momentum square to the power of 2, so Q to the 4 coming from the photon propagator. And then the last ingredient of this cross-section is this hadronic tensor that includes phase space integral over all final states. As I said before, in this example, we are inclusive in this final state. It includes the delta of energy and momentum conservation, and finally the matrix element of the hadronic current times its conjugate, and then of course sums and averages over polarizations. Now, this, depending on the specific process that we have, this current can be readily involved, but as far as we stay inclusive in the hadronic state, it is possible to write this hadronic term in a very general way using only symmetries, mostly Lorentz invariance. So all we have to do is realize that this hadronic tensor can only be constructed from a small set of tensors, which include the metric tensor, the fully antisymmetric tensor, and then the momentum transfer Q, and one of either the momentum of the initial state or the momentum of the final state, which as they are not independent, one of them is enough. And then we can write the most general structure with these tensors, and each of the monomials then comes with the scalar function comes structure function. So we see that we have 4 of them in terms which are symmetric. This is the symmetric part of the tensor, and 2 of them which are asymmetric. The structure functions are, as I said, they are scalars, and they are functions of all scalars in the problem. In this case, the only 2 scalars that one can form with these 2 vectors are the p square, which is just the mass of the target square, and then the scalar product of the momentum transfer and the target momentum. If we are in lab, this is given now in terms of the energy transfer. So these structure functions are functions of the energy transfer in lab and the 4 momentum square alone. Now, if we are dealing with electromagnetic interactions, again, only the symmetric part of the tensor contributes, at least because it's going to be contracted with a symmetric tensor, so the asymmetric part is not going to contribute. In addition, we know that the electromagnetic current is conserved, and this fact can be used to reduce the number of structure functions from 4 to only 2. So in any case, in the general situation, one can take this general structure of the hadronic tensor and substitute in the cross-section and obtain this result that you see here. In terms of 5 structure function, and it's 5 and not 6, because W6 doesn't appear in the, it vanishes in the contraction. Now, if we now neglect the mass of the outgoing lepton, as it is usually done, for example, in electron scattering, or as it will be the case in neutral current interactions, we can see that we can reduce this expression to this one, in which we have only 3 structure functions. Okay, this is a nice compact expression, which one could think it's useless because we don't know what those W's are, but it's not really so useless because you can, as you can notice here, different terms come with different angular dependence on the scattering angle of the final lepton. So this difference in the angular dependence is used in the experiment to extract this extraction function in the model independent way. I will show an example of that later. Okay, so this is the general structure of the cross-section. Now let me consider a couple of examples, simple examples. And the simplest example one can think of is the scattering of a scalar of a neutrino, neutral current scattering of a neutrino on a scalar particle. Let's assume that we have such a scalar target, right? And let's consider this process. Now, once the target is scalar, the hadronic current can only, so we have only 2 possible vectors to build the hadronic current, and no other tensors to make measures. Only the momentum of the initial particle and the momentum transfer, right? So this is the only possible structure for the hadronic current, which means, to begin with, that it is purely vector, even if the interaction is weak. At this point, since we know that the vector current is conserved, we can relate these 2 constants into one, which I have now renamed as the weak coupling. And then we have this expression here for the neutral current in terms of only one coupling. In addition, now since the initial scalar particle and the final one are the same, and the mass is the same, we can use kinematics to find that this ratio here is equal to -1/2, and use it to write the current in this very compact form. Once we know the current, using the expressions I derived before, right? So we can now write the hadronic current integrated over the phase space of the final scalar particle. We have energy momentum conservation, and then this tensor H, which is simply given by this hadronic current times its conjugate. Now we can use this structure to identify the values of the structure functions. And once we have the structure functions, I recall you that this will be the expression of the differential cross-section, of the differential cross-section. So here, remember that in the case of zero lepton mass, and this will be the case if we have a neutrino in the final state, all these terms are going to be zero. We don't have W3 because our current is a vector one. From the structure of this tensor here, we see that we only have combinations of momenta, so we don't have metric tensor, we don't have a G mu nu tensor. At the end, the only structure function that is non-zero is going to be W2. And indeed, we can just now do the algebra and write W2 in this way is 1 over the energy transfer times the weak charge square times a delta. We have a delta function because since we have a single particle in the final state, only 3 of the 4 delta functions are eliminated in the hadronic tensor. So an interesting observation that one makes at this point is that if we build the product of the energy transfer times W2, this is called the F2 structure function in the literature, it is not a function of Q square and energy transfer independently, but it's only a function of this combination of the two quantities. This is called the X Bjorken variable, and the fact that F2 depends only on X and not on Q square and omega separately is an indication that the scattering is taking place on a structureless, on a point-like state, which is what I assume from the very beginning. And if we now think of this hypothetical scalar matrix as a spin zero nucleus, then we know that the nucleus is by no means a point-like object. So for momentum transfers, which are of the order or larger than the inverse of the nuclear radius, we are going to start seeing the structure. And this has to be reflected in the expression of our structure function by introducing a form factor, which breaks the scaling that we just saw in the previous case. So this nuclear form factor is the Fourier transform of the density distribution and actually carries the information of how protons and neutrons are distributed in the nucleus. And so this cartoon here illustrates that the shape of the form factor, in this case the form factor square, is related to the density profile of the system that is being probed by the interaction. In particular, in the case of the sphere with a diffuse surface, which is the shape that is more similar to a heavy nucleus, the form factor has the typical diffractive structure. So notice that as Q increases, this form factor square is strongly suppressed. Okay, if we want the cross section for this process that we are studying, that now that we have taken into account the form factor, it is just coherent elastic neutrino-nucleus scattering, which will be discussed in the afternoon lecture. So with this example, I'm just introducing the next lecture, right? So now we have a single structure function. If we substitute it in the cross section and do some algebra, we end up with this expression of the differential cross section as a function of the kinetic recoil energy, and it is, you can see here, it's obviously it is a weak process. It's a neutral current interaction, and it's given now in terms of kinematic variables, this weak charge square and the nuclear form factor square. Now, so far I have not defined what this weak charge is, but it can be simply be obtained by recalling the structure of the neutral current in terms of quarks, which I showed earlier. So we can see that this object here is, so remember now we have a purely vector interaction, because we assume the state has spin 0, is scalar. So this is going to be the corresponding weak charge for U quarks, and this one here, the one for D quarks. So then in order to obtain the weak charge for Stevens, all we have to do is then recall that in a proton we have two protons, two U quarks and a D quark, and in the neutron one U quark and two D quarks. So and then in the nucleus we have C protons and N neutrons. So using this expression, we finally obtain the expression for Q, in which it is important to stress that this factor 1 minus 4 sine square of the weak angle is which multiplies the number of protons. So this factor is strongly suppressed. So in fact, Stevens is a process that takes place basically on neutrons. Okay, and here actually I should say that so far I assumed that the form factor is the same for the distributions of protons and neutrons, and this is a good approximation in nucleons with the same number of protons and neutrons, but it's in general not the case. So in principle, experiment like Coherent is probing the distributions of neutrons in a nucleus, at least when it goes to higher recoils. Okay, so this is the example of Stevens, which actually was a digression in this presentation, because it doesn't play a direct role in experiments with accelerator neutrinos. Let me now come to something that is more related to that topic, which is quasi-elastic scattering on nucleons. So again, now let's consider the same situation. Now with the difference that instead of a scalar nucleus, we have a spin 1/2 nucleon in the initial and in the final state. The process remains quasi-elastic, so at least in the isospin limit, we have that the mass of the initial nucleon and the final one is always the same, which implies that the energy transfer and Q square are related, so that we have X fixed to 1. Okay, then now we proceed exactly in the same way as in the previous example. We have a general expression for the cross-section in terms of electronic tensor, and a hadronic tensor that looks exactly as the one in the previous example. What changes now is of course the details of the specific state involved in the reaction. So now this H tensor is given as the trace of this Dirac structure here, which is formed using the matrix elements of the nucleon current. So this matrix elements, this current has the B minus A structure of electroweak interactions, and can be written in terms of 2 vector and 2 axial form factors. The 2 vector form factors are usually called Dirac and Pauli, and the 2 axial are called axial and pseudoscalar. So in the next few slides, I outline the derivation of the destruction of this current from general principles. I am not going to go through this in detail. Let me just, as a summary, what one does here is to write the most general expression for this current using the all possible ingredients in the Dirac algebra, and then we use Dirac algebra and the of motion, the Dirac equation, to reduce the number of structures, and then use discrete symmetries. In particular, there is a symmetry called there is a transformation called G-parity transformation, which is a combination of charge conjugation and isospin rotations, which allow to exclude also some of the possible terms that are in the literature are called second-class currents. In addition, we have T invariance that implies that the form factors are going to be real. And finally, these form factors, which are scalars, and I have functions of all the scalars in the problem. In this case, again, since Q squared and the scalar product of P and the momentum transfer are not independent in the isospin limit, then the form factors are functions of a single scalar quantity, which is the form momentum transfer square. Okay, so I am going to skip the derivation of this result, but I would like to now stress the fact that the so focus on the isospin structure of electroweak matrix elements for protons and neutrons. So for this purpose, so remember that we at the beginning we wrote the electroweak currents in terms of a hypercharge and 3 isobector currents. Now I am now in the basis in which the states are protons and neutrons, and they form an isospin doublet. So now the isobector current is proportional to the Pauli matrix acting on those doublets, and the hypercharge or isoscalar current is proportional to the 2x2 unity matrix. So what we can do then is we can write the matrix element of the electromagnetic current for the proton. Remember, it had this structure in terms of the isoscalar and the third component of the isobector flavor currents. And then this result, which I call here Vp, can be written in terms of the proton electromagnetic form factors, F1 and F2. And it also has this structure in terms of the isobector V and the isoscalar Vy currents. Now, if we do the same thing for the neutrons, since now tau3 is diagonal and has a -1 in the diagonal, what we obtain is that the isobector part changes sign. The consequence of this is that now, if we now take the charge current transition from between protons and neutrons, which is now written in terms of B1 and B2, it just, if we plug here the Pauli matrix, we can see that these combinations of B1 plus I B2 just changes a neutron into a proton. So we just get this V here from the isobector current, which from these two expressions here, it can be written as the difference of the proton electromagnetic matrix element minus the neutron matrix element. And something similar can be done for the neutron current. So the message of this exercise is very important, and is that charge current and neutral current form factors can be expressed in terms of electromagnetic ones. This is up to radiative corrections, but it's a very important result because it allows to use input from electron scattering to predict a neutrino cross-section. In fact, electron scattering on nucleon has been studied in detail in several laboratories, in mines in Europe, and more recently in Jefferson Lab. And using the scattering data they obtain, the electric and magnetic form factors, which are just linear combinations of F1 and F2, have been extracted. So the techniques used are slightly different at low Q square and at high Q square. So this data also not the most recent one, but the message I want to pass here is that there is sufficient empirical information to constrain the electromagnetic form factors on protons, and also, even if with less precision, for the neutrons using experiments on deuterium targets. So here, even the neutron electric form factor, which is very small, is constrained experimental. Okay, so now in the axial sector, we don't have this luxury. Okay, we don't have equivalent electromagnetic scattering, but still there are things we can do. If we now recall the pion decay example, in which I showed you that the weak bosons couple directly to pions. Now pions then can couple to nucleons, and in this way we can build a contribution to the axial current that go through a pion intermediate state, a pion propagator. So we can use Feynman rules to write this contribution, this matrix element of this contribution to the current is written here in terms of the pion nucleon coupling, which I call here GNN pi, and then a form factor that is normalized to 1 at q squared equals 0, which accounts for the structure of this vertex, because here we have particles which are not point-like, so there will be, let's say, higher order corrections of the tree of the vertex that are included effectively in this form factor. So we can then apply now Dirac equation and end up with this result, and we can see that what we get from this diagram here is a contribution to the pseudo-scalar form factor, which is, well, it is no surprise, because we knew that this coupling here is proportional to the momentum transfer, and this is the structure that appears in the term proportional to the pseudo-scalar form factor in the axial current. So we also see that this term has a pion propagator, and as the pion is light at low q square, the pseudo-scalar form factor is going to be enhanced. Okay. So what we can do then next is go to the chiral limit, taking advantage of the fact that pions are light, and use the fact that in this limit the axial current is conserved. By doing that, we find that in the axial limit, in the chiral limit, this axial form factor is essentially related to the pion nucleon vertex. In particular, at q squared equals 0, we know that the axial current is going to be equal to the pion nucleon coupling. So this relation, which is called Goldberger-Treyman relation, is remarkable because it connects electroweak physics with pion nucleon scattering. In the case of this process, this is not very relevant, for example, to predict neutrino cross-sections, because GA is measured from beta decay, but this is still very, very important, because equivalent Goldberger-Treyman relations can be derived, but for different processes, and in those cases the couplings are not known, and then information from pion nucleon scattering can be used to extract those couplings. So again, this result here is exact only in the chiral limit, but corrections to that to this result are going to be proportional to powers of the pion mass, and therefore are going to be small. So corrections of the Goldberger-Treyman relations are of the order of a few percent, maybe 1 or 2%. So if we assume, if we neglect this correction, it is possible to then write the axial current of the nucleon in terms of single form factor, which is the axial form factor. And here we can see that the pseudoscalar form factor has the pion pole, which has actually been seen clearly in muon capture experiments, and that has also been observed in the results from lattice QCD. So then the only ingredient, if we now want to predict quasi-elastic cross-sections on nucleons, the only ingredient that we have left is the axial form factor. So what do we know about the axial form factor? We know very well GA, again, as I said before, from beta decay. We also know from perturbative QCD its asymptotic behavior. In the intermediate Q-square range, we don't know this form factor so well, because the only reliable information that we have comes from all bubble chamber data with poor statistics. Nonetheless, this form factor has been extracted from this data using different parametrizations. The most common parametrization is the dipole parametrization, in which the Q-square dependence is parameterized using a single constant called the axial mass, right? This is the simplest parametrization, but there are some issues with this to begin with, because it has no theoretical justification. So it's not solid from that point of view, and it's not flexible enough because it is just one parameter. So there are alternatives. Some alternative parametrization of the form factor of these form factors have been derived, and to make the story short, all the methods tend to give the same Q-square dependence, but have different estimations of the error associated with the extraction. And this ultimately is due to the fact that the data have poor statistics. So the message of this slide is that this cross-section, which is very important for neutrino experiment, the modeling of quasi-lattice cross-section would benefit a lot from new measurements on hydrogen and deuterium. Actually, here this is also a place where lattice QCD could be very helpful, and where the lattice studies are more advanced. Okay, so now this was all for nucleons, but as I said at the beginning, modern experiments all have nuclear targets in their detector. In that case, we have now a situation in which the target is a multi-nucleon system, and what we immediately see is that from this plot here, this peak here indicates quasi-elastic scattering. This is x equal to 1. Now, when we go from here to finite nuclei, this sharp peak becomes a broad peak called the quasi-elastic peak. Then below the quasi-elastic peak, we have number of broad peaks coming from giant resonances, which are collective excitations of the nucleus. Then there are peaks with energies of a few tens of MeVs, which correspond, or even less, which correspond to discrete states. And finally, we have a peak here, which is elastic scattering, which in the case of neutral current interactions is going to be Siemens. So we see that when we have nuclear targets, there is a much richer structure, or zoology, if you prefer to call it this way. And all of it is ultimately due to the fact that we have nuclear-nuclear interactions. So the nuclear-nuclear interactions have several remarkable properties. I'm not going to elaborate much on them. Let me just mention a few details. First of all, as it is well known, it is short range, so it is it goes to 0 for already. It is 0 for internucleon distances of around 3 femtometers. Then it has an attraction at intermediate distances, slightly above 1 Fermi. This region here is dominated by the exchange of pions between nucleons. But then this attraction turns into a very strong repulsion at short distances. The consequence of this is that nucleons cannot get too close to each other. So therefore, if we keep adding nucleons to the nucleus, so we go to heavier nucleus, the density in the center of the nucleus nonetheless remains more or less constant and equal to the saturation value, which is around 0.16 Fermi to the power of -3. So this is a remarkable property of nuclear systems, and the consequence of it is that at this saturation density, the distance between nucleons is the average one is around 2 Fermis. So therefore, the nucleon-nucleon interaction is kind of weak, amazingly, but it's kind of weak inside nucleus. Therefore, as a first approximation, it is possible to describe nucleons in a nucleon as narrow, almost, not quite, but almost on-shell states, following single particle orbits in a mean field potential created by all nucleons. The simplest realization of this scenario is the situation in which we don't have any mean field, so no potential. In this case, we have the nucleons which are plane waves with a given momentum, but since they are fermions, they cannot all have the same momentum. So nucleons start to occupy all possible values of momentum until they reach the maximum momentum of you occupied all the states for the number of nucleons that you have, and this maximum momentum is called the Fermi momentum. So the distribution of this number of states, these occupation numbers in this very simple model, which is just the Fermi gas, is just that this occupation number is constant up to the Fermi momentum, where it goes sharp to 0. So we have a step, and the value of the Fermi momentum can be estimated, for example, taking the density, so summing over all the states, and then this is going to be equal to the density. And if we take the saturation density, we can obtain that the Fermi momentum is of the order of 250, 260 MeV. So how is this used to calculate neutrino cross-sections? Well, this can be illustrated, for example, in the green function formalism, in which we can see that if we now write the propagator of a single nucleon in such a medium which is just a Fermi gas of non-interacting nucleons, in that case the propagator, even if there are no interaction, is not just the vacuum propagator, it has a second term, and it can be split into two contributions, one called the whole part and the other one called the particle part. So this terminology is borrowed from condensed matter and simply implies that when an external probe interacts with such a Fermi gas, it interacts with a single nucleon and kicks it out from the Fermi sea. So it has to be kicked hard enough, so because it cannot go into an occupied state, it has to go to the continuous. So, and then in that case, it leaves a hole in the nucleus. So with this simple picture, it's it is possible to describe the gross properties of nuclear response, but it is too simple to describe the details. So it fails with the details. In order to be more accurate and ultimately meet the needs of modern neutrino experiments, one has to take nuclear-nuclear interaction explicitly into account by introducing a mean field, and also by taking into account the nuclear-nuclear interactions between nucleon pairs, which are called correlations. A way to see how this can be done is that then in presence of nuclear-nuclear interactions, this nucleon propagator in the medium that I have shown here, be rewritten in terms of so-called spectral functions. Spectral functions which are nothing but the imaginary part of the full dressed nucleon propagators of particles and holes separately. So this is the general expression of spectral functions. You can see here that they have the form of, again, the imaginary part of propagators, including the self-energy. So sigma here is the nucleon self-energy coming from the interaction of this nucleon with the rest of the nucleons. In particular, you can see that the imaginary part of the self-energy goes to 0. So this spectral function becomes a delta function, only modified by the real part of the self-energy that accounts for the mean field. So the imaginary part of the self-energy is now going to be responsible for the broadening of the state, from the departure of the state from an isolated delta function, and this is what is called correlations. Okay, now spectral functions can be integrated to give the occupation number, the same occupation number that in the case of the Fermi gas is just a step function. Now, when we take realistic nucleon interactions into account, what we obtain is a picture like the blue curve here. So actually, this is not the occupation number alone, it's the occupation number multiplied by the nuclear momentum square, because this is the way in which it appears in observables. And what you see here, first of all, is that the result from the naive Fermi gas that I described before is just constant up to the Fermi momentum. So we have this parabola, this p square, up to the Fermi momentum, and this goes to 0. This is very different from what we obtain by the blue curve. The Fermi gas model can be improved using the local density approximation, in which the density depends on the coordinate, and then empirical experimental density profiles are used. This is the local Fermi gas. We can see here in black that this profile is much closer to the realistic one for the local Fermi gas. But what it doesn't have is this long momentum tail that is seen here in the blue curve, that comes from short-range correlations. So the study of short-range correlations is a science in itself. It's studied at Jefferson Lab in detail. With neutrinos, what I want to say now, that with the caveat that the statistics tends to be limited, neutrinos are ideal to study short-range correlations because for reasons related to the isospin structure of the nuclear interactions that I don't have time to cover, these short-range correlations appear mostly in pairs of neutrons and protons, so two different isospin. Then if you interact, if a neutrino interacts with such a pair, it's now going to turn this neutron into a proton, and as a result, in the experiment, one can see two protons back to back in the laboratory frame. In fact, events like this have been observed by the Argonaut experiment. The statistics is totally insufficient to do a detailed study, but they have identified these so-called hammer events, in which one can see the track of the lepton going forward, and then two protons going back to back, which would be the same signature of such short-range correlations. Now, the last thing I want to mention at this point is that apart from correlations, there are other ways in which external probes can interact with nucleon pairs, which are called meson exchange currents. So those are interactions in which the external probes interacts with the two nucleons, which are again interactions through the exchange in this example of these Feynman diagrams, through the exchange of a pion. So this kind of mechanism called meson exchange currents, they are allowed by symmetries, and they have a sizable contribution that has been inferred from data on inclusive electron scattering. So it has been seen that the contribution from these meson exchange currents fills the dip between the quasi-elastic peak and the inelastic peak, where the pion threshold is open and one can produce mesons. So this has been seen in electron scattering, but also several different calculations. Here are the two examples, have identified that this mechanism is required to describe mini-boom double differential cross sections, which otherwise would, in order to describe them, one would need to alter the axial form factor, increase its slope in disagreement with what is found from bubble chamber experiments on hydrogen targets. So this finding is, as I mentioned at the beginning, interaction with a couple of nucleons are very important for oscillation measurements, because they can falsify, they can bias energy conservation. So at low energies experiments in the region of mini-boom and now T2K, these interactions are well under control. In the case of fluxes with heavier energies, there are some discrepancies. I show you at the beginning what happens at NOVA, where there is an excess that they attribute to mismodeling of this contribution, and something similar happens in Minerva, where here you can see they have this excess compared to the Monte Carlo. It is not yet clear what is the ultimate origin of this excess. It could be that the theory is incomplete for the kinematics probed in these higher energy experiments, but it could also be that the implementation of this mechanism in Monte Carlo. So let me remind you that up to a few years ago, this mechanism was completely absent in Monte Carlos like Gini. So their implementation is still very primitive. So it could be that part of the reasons of the discrepancy is due to the implementation and not the theory alone. And again, as I said, and with this slide, I'm going to come to the conclusions. It is very important to understand those mechanisms, because they bias neutrino energy reconstruction. Now, at this point, I have several slides devoted to inelastic scattering, which I have included in the slides. If anyone wants to check, I was sure I could not possibly cover this. So let me come now to the slide where I list what I couldn't cover in this lecture. Again, is inelastic scattering on nucleons and heavy nuclei. It is in the slides. What is not in the slides is deep inelastic scattering, and something which is very important for Dune and still poorly understood, which is how one makes the transition from the resonance regime to the deep inelastic regime. So this is not understood. Another interesting topic which I didn't cover at all is polarization observables. Polarization is relevant, for example, in tau appearance measurements, because the tau polarization is used to, it helps identifying, distinguishing between the products of the tau decay and high energy neutral current interactions. So from the distribution of the decay products. And in addition, polarization observables, they are interesting because they provide stringent tests for the models. And my final slide is just a list of test books, monographies, and a couple of reports that I have used in the preparation of this lecture, and where you could find material that is related to this topic. So this is it. If there are questions, I'll be happy to answer.
Francesco, go ahead.
Hi, Professor. Thank you very much for your presentation. That was very interesting. I have a question. I posted in the chapter, page 8 of this presentation. There is the neutrino cross-section from 10 to the -1 to 10 to the 2 GeV for neutrino. My question is, why does this plot look different from the one you showed? I mean, this one is pretty old, so this might be the reason, but just for curiosity.
Well, I'm opening it. I'm not sure. I'm not sure which plot you have in mind. In the meantime, while it okay, this is Minerva. Which page?
8.
8.
Yeah.
So in page 8, you have the cartoons with this cartoon with the cross section, right?
Yeah, because for what I remember from the slide you presented, I mean, the quasi-elastic peak was a bit was more on the left side, and so the resonance one, but maybe I misunderstood it.
I mean, I'm sorry that for the rest you don't see this plot, but this is a very common cartoon for neutrino interactions. Perhaps I can share the screen so that the others can see. If I see how to do this. Okay. Oh, you can look. Okay, you have it in this. Yeah, right. Maybe this is indeed faster. Indeed. So page 8. So we see what we see in red at lower energy. So this is to begin with. Let me mention that this plot is kind of nice because it summarizes the different cross sections, but it can be misleading because it's plotted as a function of the neutrino energy, and what ultimately matters for the interaction with nucleons or nuclei is the energy and the momentum you transfer to the target. Obviously, there is a relation. If you have higher neutrino energies, you can transfer more momentum. But anyway, so the curve in red is quasi-elastic scattering. It appears at low energies. The plot I was showing is not as a function of neutrino energy. It's perhaps this is what confused you.
Yeah, I think so. I realized you were showing, yeah, the momentum. Yeah, sorry for that.
I was showing a double differential cross section for mini boom. So it is, if I can, sorry, it's a bit slow. So this is the plot for quasi-elastic scattering of quasi-elastic-like scattering at mini boom. So this is a selected double differential cross-section slide. So this plot is a double differential cross-section shown as a function of the muon energy for a window of angle. So it is differential. There is a plot for mini boom showing the integrated cross-section, which I don't like to show because it's misleading, simply because mini boom, in order to show the neutrino energy dependence of their cross-section, they had to assume that the process was purely quasi-elastic in order to reconstruct the neutrino energy. But we now know well that this assumption was not entirely correct, that they have a sizable contribution from two-nucleon mechanism which distorted their energy determination. So I hope this answers your question, but if not, just keep asking, please.
It does answer. Thank you very much. I was confused indeed.
Any other question? No. So thank you, Luis, for this very comprehensive talk. And now probably Avelino should say something. We should get back, I think, at the 3, but if you have any announcement or whatever.
Well, no announcement, but you are correct. So we are back at 3, and there will be a lecture from Kate Scholver. So thank you.
So